Is the graph that of a function? If so, state the domain, range, intercepts, and symmetry. All right, so let's start with example A. It looks like we have a piece of a function that goes from negative pi to pi on the x-axis and goes on the y-axis from -2 to +2. Now, in order to test to see if it's a function, we can employ something called the vertical line test. The vertical line test says if we run vertical lines through the graph, right, that these lines will not intersect the graph in more than one place if it's a function. So in other words, as long as the lines intersect the graph in at most one place, this graph is a function. So we can see that if we ran these vertical lines through the graph, they only intersect the graph in at most one place. Okay, so it looks like A is certainly a function. The other thing we can determine from it is that it looks like the domain for the function is basically from -pi up to pi. The reason why I say that is because on the x-axis we go from this point here to this point over here, and those points are actually obtained on the graph. In other words, there is a point right at -pi and a point right at pi. So I include brackets here to show that I'm including those points and that the x-axis values range from -pi to pi without any exception, right? So the line is unbroken. It's continuous from this point all the way over to this point, and basically we can show that there's a point all along the way at any fraction or decimal between those two values, -pi and pi. All right, likewise, the same thing is true for the y-axis. It looks like for the y-axis, or in other words, the range of the function, we can see that the graph goes from -2 here, right? -2 up to +2. So the range is going to be -2 to +2, and again, inclusive, so I'm going to use these brackets here. And I use the brackets because we actually have a point that has a y-coordinate of -2 and a point that has a y-coordinate of +2. And again, there doesn't seem like there are any points missing, right? So in other words, all the way through from this high point, this maximum over here, down to this minimum over here, it looks like there's no break between the points, right? In other words, all along this graph, you have corresponding y values, right? So it appears that the domain is -pi to pi, the range is -2 to 2. All right, from there we have to look at the intercepts. Well, we can see that the y-intercept, right, occurs right here at the origin. So I'm going to say the y-intercept is at 0, 0. All right, so let's look at the x-intercepts next. We can see that there are actually 3 x-intercepts, right? There's an x-intercept here, and that looks like it occurs at -pi on the x-axis, right? And 0 on the y-axis, right? All x-intercepts have a 0 y-coordinate, remember that. So then we also have the origin again, so 0, 0. And then finally we have this value here, which is basically at pi on the x-axis and 0 on the y-axis. So those are your x-intercepts. And lastly, there's the question of symmetry. So for symmetry, it's actually a visual thing. You know, we can check to see that there's no x-axis symmetry because notice how there's no corresponding point over here, right? If I folded the graph over across the x-axis, this point here would not be replicated over here. So that means that there is no x-axis symmetry. Likewise, if I folded it across the y-axis, right, this point does not exist over here, so there's no y-axis symmetry either. All right, so the last symmetry to look for is origin symmetry, and it appears that it does have origin symmetry actually. So it looks like for any point x, y on the graph, there's another point -x, -y on the graph that matches it. So we're going to say origin symmetry for this graph. All right, so let's look at the next one. The next one is the graph for B. And first thing we want to do is to determine if it's a function or not. Remember, we use that vertical line test. And you can see if we ran vertical lines through the graph, they will intersect the graph in at most one place. And that means it passes the vertical line test, so it is indeed a function. Now from there, we can see that the domain for the graph, in other words, the possible x values, are actually going to go from -infinity up to +infinity for this graph. So we'll say the domain here is from -infinity to +infinity. The reason why I'm saying that is it seems like this is going to continue to broaden outwards, right? Forever and ever. And as it does that, it'll gradually cover every possible number, right? So it looks like it definitely has a domain that runs the full gamut of the x-axis. Now what about the range? Well, for the range, we just have to consider what's going on the y-axis. it doesn't look like we have any points beyond this point here, and that's at y equals 2. So that means that the maximum value for the y is positive 2. But what about going down? It looks like it goes down and down and down forever, right? It's going to go down forever, and we're going to have, therefore, every y value below 2. So the range should go from negative infinity, always with a round bracket on negative infinity because we don't want to include infinity, right? You can't include the concept of forever small or forever big. But we will go up to 2, and we will include that, right? We'll use a square bracket there because we're going to say there actually is a point on the graph that has a y-coordinate of 2. All right, so the domain and range are written out there. From there, the next thing we want to do is to talk about the intercepts. The intercept for the y-intercept is labeled nicely for us. The y-intercept is just 0, 2, right? So that's labeled on the graph already for us. It doesn't intercept the y-axis any other place. There are actually 2 x-intercepts. We can see those as well on the graph pretty nicely for us. The first x-intercept is right here on the left. It looks like that might be -1, 0. So -1, 0 is what we'll assume. And for the other x-intercept, we're going to look at the second point here that crosses the x-axis, and that looks like it's occurring at 1, 0. So x-intercepts are there. Lastly, we have to consider the symmetry. If I folded this graph right down the y-axis in half, this point would lay on top of this point would lay on top of that point, so on and so forth. So we have perfect y-axis symmetry here. So that's a y-axis symmetric graph. That's for sure. It doesn't have x-axis symmetry though, right? If I folded it across the x-axis, obviously the graph is not going to have a mirror image everywhere, right? There's not a corresponding point over here. So we're going to find that x-axis symmetry fails, and origin symmetry will also fail. If you look at a point that occurs in the graph, say one point right around there, the way we'd get there from the origin is we go to the right and then we go up, right? So we go to the right and then we go up. If we did that same movement or the opposite of that same movement, so in other words, we went left and then down, we don't find a corresponding point here, right? The graph isn't going to match up there. So we don't have origin symmetry there. Or even if you took a more extreme example, say a point right here, right? That point on the graph. To get there, you have to go to the left and then down, right? Well, if we went the same distance but on the positive and then went up, we certainly don't find a matching point here, right? It's missing. So that means there is no origin symmetry. So the bottom line is this graph has only y-axis symmetry. It has the domain and range we specified there. And of course, we have the y-intercepts and x-intercepts that we listed here.